All right, so this is a review session for the test on enzymes, which is the next class. But I think that's a good question. Let's first of all go to exactly what the practice was that was needed for this, and then I'll show you exactly where stuff was, okay? So that's a good question. Let's start with that. All right, so this was the slides that were up today. You remember that. So, but if we go back, here we go. Okay, so this is a list of the practice work, not the lactase enzyme stuff, but the practice work that was needed for this. And there wasn't very much, and most of you already got most of it done. I didn't have an Aspire to do. I took that away. There is a history quiz in Albert IO. It's waiting for you. There was one ed puzzle, Mr. Anderson Explains Enzymes. There was the guided reading, and those I put up a long time ago. A lot of you have done that already. The paradox on enzymes, you all have that because you did that in class with me, so you have that. I don't think anybody didn't do it, so you're all fine. The free energy graph worksheet. I think, Dua, you're asking about this one, the titling activity worksheet, that one right there?
Yeah.
Yeah, okay, so let me go take a look at, show the Google Classroom and make sure that it's there, because it should be there. But maybe, let's just make sure. Okay, so this is 6th period. Dua, are you in 8th period?
Yes, I am.
Okay, so in 6th period, yes, titling. No, it would be down here. Okay, so in enzyme structure and function, it's in that folder, not in the lactase enzyme folder.
Oh, okay, got it. Yeah.
It's right there. It's right here, right? And it's just one page, and it's actually I didn't wind up going into that as much as I had intended to be. It kind of got lost by the wayside, but you can still do it, and it's right there. And okay, and it's due Friday, so you have some time.
Okay, makes sense. Thank you so much.
Oh, no problem, no problem. That's why this is good to ask these questions. To find all the things, all the practice items that were just on that list I just showed you, this is where they are. They're in the Unit 3.1 Enzyme Structure and Function folder, right? So there's the paradox, there's a copy of it there if you needed it. There's a YouTube of me talking about it. There's your free energy graph worksheet. Well, there's a key for it. So if you needed the answers, there they are. The worksheet is here, right? The one that you needed to do. The only other thing that was, here we go. So the ed puzzle and Mr. Anderson's down here, right? And there's the guided reading. And then you had a guide for cell energy, which I'll show you in a second too, just to show you what's actually going to be on the test, all right? Okay, so it's everything that you need to do in terms of practice is in this folder. Everything that you needed to do for the lactase enzyme is in this folder, right, which you guys have already been working on, right? So the HHMI ed puzzle is in here, the make your 2 graphs thing is in here, and then your group thing that you just did, that you guys, if you're in 8th period and 6th period, you guys did that, right? 7th period, you haven't done yours yet. That's next week for you. But all the practice work for all of you is due Friday, right? The practice work is due Friday. And 6th and 8th period, your lactase enzyme stuff should be done now. You should have it all done now. 7th period, you guys won't be finished until next Tuesday, right? Okay. But the biggest ticket item right now, I understand, is to get you through the test, the enzyme test, which is tomorrow and Friday. So let me switch over to the actual guide. Yeah, okay. Okay, that's a good question. In terms of what the analysis looks like for the little titling activity, like pretend you're just writing a short claim for each one, okay? Just one sentence is fine. You don't have to make a big paragraph. I'm not looking for that. Just this is graph showing, okay? Just a claim is fine. Sophie, yes?
Would it be possible to put up another try on the Albert quiz?
There should be 2 tries for you.
Okay.
Is there not? There should be.
I'll double check.
Yeah, as far as I know, there's 2 tries for all the classes. If there's not, let me know, okay? Let me show you the actual guide that tells you what's on the test now. I'm going to share that next. Let me just do that. Here we go. Okay. There we go. All right, there. Okay, so now you should see what's on the screen. Let me make it a little bit bigger. Get bigger. This was easier to make bigger. Let's make this. That's a little better. Maybe a little bit more. Boop. Ah, there we go. Okay, so this is the guide for the entire cell energetics unit, but we divided it into 3 parts, remember? So this is what's on your test tomorrow and Friday, Unit 3.1. This is what we've been working on for the last 2 weeks, right? So let me tell you what's not going to be on it, because we didn't talk about this, okay? Don't worry about that. Don't worry about any of, oh, that didn't mean to do that. Don't worry about these things. Allosteric regulation, inhibitors, cofactors, feedback inhibition. I'm not asking that because we didn't go over it. Everything else, though, here, we did. We did all these other things. So enzymes, substrate, active site, activation energy, induced fit, environmental impacts. We certainly did a lot of that, pH and temperature, and denaturation. You should know all those things. And then we did talk a lot about the laws of thermodynamics, right? We did a whole presentation on that. Free energy, entropy, exergonic versus endergonic, and the graphs and everything that's in those graphs. So there, right here, this is kind of a good blurb that tells you what's going to be on this enzyme test, right? So now let me go to back to your screen with you. Okay, so what's in yellow there? Again, I'm saying that what's in yellow, I'm not going to ask because we didn't talk about it, right? Now I'm going to go to a white worksheet here. Okay, so let me just review those free energy graphs with you for just a minute. Let me see how much you can remember about those, because there's definitely a couple of questions on those. So if you have a graph, a free energy graph, that, let's say it looks like this, like this, okay? And so let's just add a couple things. You see the reactants are over here, and the products are down here. Right? So you should remember that, yes? Now let me see, I'm going to ask you some labeling questions here. I'm just going to draw some kind of dotted lines here, just for reference. Okay, things like here. All right. So what is this value right there? That arrow that I just drew right here. How would you label that? Which variable should go there? Yes, that's it. Beautiful. Okay, so if I were going to draw it, I'll just draw it here. So this is delta, which is often a triangle, G. Delta G. Okay, and delta G is defined as the change in free energy between the reactants, the energy stored in the reactants, and the products. And if the graph looks like this, right, where the reactants have more potential energy stored in them than the products, is delta G negative or positive? Negative, excellent. Yes, that's right. Okay. And whenever you have a negative value of delta G, would this reaction be exergonic or endergonic? Yes, we are releasing energy. That is right. Okay, so this is an exergonic energy releasing reaction, because the reactants, the stored energy in the reactants, those molecules were rearranged and changed into the products, and the energy difference is released, right? Sorry, my squiggly line. So energy was released. the energy that is no longer in the products, it got released into either released into the environment as heat, or it was, well, I wouldn't word it that way. In terms of you're not producing energy, you are releasing it, right? So the energy that was stored in the reactants, when the reactants were broken apart and changed into products, that difference in energy was either stored into new molecules, like in some cases you might have put some of the energy into an ATP molecule, or it was released as heat. You always have a bit of energy released as heat. So it just, the energy that's released here could either be put into some other storage molecule that isn't in the products, or could be released as heat. Okay, I'm going to keep adding to this because there's more to this picture. So now, let's say that that this exergonic reaction went through. What would this symbol be? What does that symbol represent right there? That's entropy. Very good, Mina. All right. So this is entropy. And what is entropy defined as? This is entropy. Good. Disorder. Yes, that's it. Increased chaos. Yes, both of those are right. Okay. And a lot of times, a very, very common source of entropy is heat. Another source of entropy is if you have lots of smaller molecular products than you did with the reactants. Like if you had a big molecule here that turned into lots of little molecules, then you are increasing the entropy. And therefore, in most exergonic reactions, most of the time, your entropy is a positive value. So when delta G is negative, right, when you're releasing energy, very often, you are increasing entropy. So that's another symbol that you would need to be able to associate with these graphs. Okay, I'm going to put one more thing in here. The difference between adding an enzyme to this reaction and not adding an enzyme to the reaction. So let me draw a red line in, and let's say that this red line, that red line right there, represents adding an enzyme to this reaction. So as a result of that, what does the enzyme reduce by being added to the reaction? Activation energy. Excellent. Okay. And activation energy with the enzyme would be this value right here. The line between the reactants and the topmost level where the transition state of the reactants is. That's activation energy. And the way we draw it is as an E sub A is how they draw activation energy. And this would be the activation energy with, there we go, with enzyme. Right? So with the enzyme, you have this activation energy. Without it, the activation energy is this amount here, right? So this would be the activation energy without enzyme, okay? Without enzyme. There. Okay, that's pretty good. Now, do you notice that whether I add the enzyme or not, let me ask you this question, this is on the test, okay? With or without the enzyme, is the change in energy different? Very good, that's correct. So the enzyme does not change the amount of free energy that can be released or absorbed by the reaction. All the enzyme does is change how fast the reaction can go because it reduces the amount of activation energy necessary. Do you remember how the enzyme physically does that? what is it about the enzyme that makes the activation energy lower, that makes the reaction more efficient? What is it physically, the enzyme molecule, that speeds up the reaction, makes it more likely to happen fast? Excuse me. Well, the enzyme is made of proteins, yes, is made of a single protein. So, I mean, if I were to draw an enzyme here, let's say that's an enzyme, okay? And the entire enzyme is a protein. It's a single, or maybe two polypeptides, but it's a single protein, right? What is this pocket here? What would you expect that would be? That's the active site, right? So it's the three-dimensional shape and the chemical nature of the active site that's really making the reactants react more efficiently. And remember, there were all kinds of ways in the pear deck that we talked about how the active site does that. We even watched a video that showed you the inside of an active site and how its chemical and ionic and pH nature actually perfectly fits the shape of the reactants and causes those reactants to be lined up just right so that they can become the products, right? So that's what's really happening here, is you have an active site here that has chemical properties and a perfect shape that specifically fits the particular reactants, or we could call them substrates too, okay? Reactants, substrates, same thing. That fits them right in there and allows the reaction to happen more efficiently, right? But it doesn't change the overall delta G. That's always the same, regardless of whether the enzyme is there or not. It changes the EA values, the activation energy value, but it doesn't change the difference in free energy. Okay, so for example, this reaction here, could this reaction, let me ask you this, would this reaction be more likely to be photosynthesis or cellular respiration? Very good, yes, this would be more likely to be cell respiration, which is very much an exergonic reaction, which is taking big molecules like glucose and breaking them down into lots of little molecules, and in the process taking that energy and storing it into ATP, right? Okay, good. So now if we erase this, we redraw it this time, and this is also a free energy graph, but this time it's going to look a little bit different. Now what if I start down here and I go up here and I wind up? Yes, Hannah.
Hi, sorry, this is kind of more about the last thing, but if you have like two substrates reacting, is the reaction always exergonic, or can it be like exergonic and endogonic?
You mean if you had two substrates reacting and you were putting them together, like a dehydration synthesis reaction?
Yeah.
Okay, so that's a really good question. Glad you asked that. If you have two substrates that are being bound together, then you are actually, that would be endergonic.
Oh.
Almost. Because you're taking two pieces and it takes energy to put them together, and you're decreasing entropy. And yeah, that would be an endergonic reaction almost always, if you're taking lots of things and putting them together into a larger thing. Usually that's going to be endergonic. Our lactase enzyme lab was about taking a disaccharide, lactose, and breaking it into parts. So the lactase enzyme is doing a hydrolysis reaction, which is exergonic.
Oh, okay, that makes more sense.
Yeah, aha moment. That was an excellent question. Thank you.
Yeah, thanks for explaining.
Good, excellent. I'm glad we make that connection. Okay, so now I've got another graph here that is also a free energy graph. So let me kind of put the same delineations in as I did before. Okay, I'm just going to mark off the levels of the products and reactants here. All right, and in this case, once again, this arrow that I've just drawn, what value is that? Which variable is that? Delta G again, very good. So I'm going to put a delta G in here. And this time, the change in free energy, is it positive or negative? Now it's positive. Very good. Yes. Okay. So this time, energy is absorbed into the reaction. We need to kind of, yeah, there we go. So we kind of are reversing the way we're thinking this time, right? So now you need to absorb energy. You have a positive delta G. So now are we endergonic or exergonic? Endergonic, beautiful. That's it. There we go. Okay, so this is an endergonic reaction, this whole thing, this whole graph. So positive delta G. What about, oops, what about this guy here that we talked about before? What the heck is that? I don't know where that line came from. What about delta S this time? I don't know what that line is, ignore it. Is delta S going to be increasing or decreasing? Very good. Yes. So this time, yeah, it flips the signs. Your delta S, your entropy is actually decreasing, and your delta G is increasing. Yes. So so this might be a case where you have something like photosynthesis happening, right? So this might be photosynthesis, for example, where your reactants might be carbon dioxide and water molecules being built into a single glucose molecule. And so your chaos is decreasing because you're taking lots of little things and building them into one thing, right? Which is organizing, which takes energy to do. So in the case of photosynthesis, a lot of the energy input is coming from light, for example. Okay, so now let's keep going with the delta. Let's talk about activation energy, because this is a very different looking graph than that other one that was exergonic that we talked about before. So what do you think the activation energy would be here? Would it be, let me just here. Would this be your activation energy, or would this be your activation energy? Yes, very good. That's a very, very easy question to miss. So I want to make sure I explain that. So this literally all the way from the reactants, where the reactants start, to where your transition state is up here, that whole thing is your delta, I'm sorry, your E sub A, which is your activation energy, right? Yeah, there. So consequently, if you added enzymes to this, you could still reduce it, right? You could still have, your activation energy is a little bit lower, but it's still much higher than the exergonic reactions, where your reactants start up here and then go down there, right? I just wanted to make sure you knew where your activation energy might be in a reaction like this. So that red arrow would be your activation energy with enzyme, and the black one next to it would be activation energy without enzymes. Okay, so that's a pretty good free energy graph review. Would you like to play a Kahoot? Yes, okay, I'm going to start a Kahoot. Just go to that. Kahoot time, yeah. I think the Kahoot that I found is a nice one. So let me just go get it started. I'll be right back to, hold on, here we go. Just get to yeah, there we go. Page classic. All right, I'm going to share this page. And be able to hear the music. Let me just go there. It's kind of loud. I think it's this one. Yes. Okay. Let me pull that down a little bit. That's a little bit loud. There we go. Okay. Okay, you can see it. Good. All right. So go ahead and join, and we can try this. Okay. All right. Excellent. Okay. Okay, are we getting everybody? There are 8 of us here. Okay. Right. Okay. All right, let's start. All right, great job. Nice job. All right, Emma, good job. Let's try another one. This is a good little factoid. Yes, it ends with ace, but it's named after the substrate. So like lactose becomes lactase. So not after the cell in which it's found, but after the substrate that, that it works on. Okay, good thing to know. All right, Mina, good job. Think about the term induced fit, right? Induced fit. And what does that look like? So it's actually accepted both of those, so that's fine. It really should be more of the active site changes to accommodate the substrate fit. So the orange one is really the better answer. But fitting in the lock and key hypothesis is something that they had when I was going to school, and it's less accurate than the orange one, although they're both counted as right. Oh, Emma's on fire. Think about this one. Yeah, that was false. Yeah, the activation energy doesn't, is not supplied to make the enzyme's active site the right shape. No, the activation energy is the energy you need to get the reaction started, which can be affected by the presence of the enzyme, right? It can either be high or low depending on whether the enzyme is there. But yeah, that's an incorrect definition. So good if you caught that. Okay, good. So what does very high heat cause to happen? Yeah, it alters the active site of the enzyme. If it gets hot enough, it denatures it so it can't work anymore. Excellent. Okay, good job. Ah, you guys got that one. Excellent. Yes, enzymes are made of protein. Okay, Emma's still on fire. Nice job. Yeah, don't overthink this one. There you go. Yes, substrate. That's it. That's all they wanted. That's good. Okay. Good job. Good job. So really strong sulfuric acid is going to lower the pH to like 1, for example. What will that do? Yes, it will denature it. Yes. Increases activity? Probably not. Really, really strong acids tend to destroy the shape of most enzymes. It just pulls them apart and unravels them. Yes. Okay, good. Which one of these is an enzyme? Thank you for getting that right. Excellent job. Okay. Good, good. I like how you're taking your time to read it. Good for you. That's good. Yes, that's right. Enzyme molecules are specific in their actions. So if an enzyme can work on egg white, but it doesn't work on starch, that speaks to enzyme specificity. That's all. Good for you for taking the time to read that. Dua, you are on fire. 10 correct answers. Wow, awesome. Okay. It's kind of small. I'm sorry about that. Didn't realize it would be so small, but yeah. Yeah, that's it. It just varies with pH. They showed you 4 graphs that were all about how different enzymes respond to pH. Yeah, that's right. That's good. Good. Optimal, best, right? This is right out of what you just did today, right? Yeah, so body temperature is around 37, so this must be an enzyme that's working in the body. That's good. All right. An enzyme substrate complex. Which of the pictures shows an enzyme substrate complex? That's it, right? Yes. Okay, so here, let me go back to this. There it is right there, right? So this thing is the enzyme. Here it is by itself. And this is the substrate. And here it is when it's after it's broken up, right? So when they're together, that's called an enzyme substrate complex. It's no more mysterious than that. Okay. Okay, not bad. And Hannah's on fire. Yay. So X is in white, if you're having trouble seeing that. The X is in white. So what would molecule X be? Yeah, okay. So yes, a catalyst is another word for enzyme. If you were confused about that. So here's the picture, and they wanted to know the identity of this molecule X here, right? Which is the enzyme, right? And in fact, this is exactly what lactase enzymes do. Is a lactase enzyme accepts a disaccharide like lactose and breaks it apart by hydrolysis without being changed in shape. So if you didn't realize that catalyst is a synonym for enzyme, now you know that. That's a good vocabulary word to know. Okay. All right. Okay, good. Reese, all right. Answer streak of 4. Nice job. So H2O2 is hydrogen peroxide. And you have this enzyme catalase that breaks it into water and oxygen. So the question is, would this prevent accumulation of hydrogen peroxide? And yes, it would. Yes, that's right. That's exactly what it would do, because it's breaking it down into harmless water and oxygen gas. So yes, that is a true statement. Nice job. Okay. Okay, same picture again. So catalase acts as a what? Good vocabulary here. Yes, hydrolysis is what's happening of hydrogen peroxide. Synthesis, you're not making it, right? Because if you look at this, you are breaking it apart. You are hydrolyzing it. So this is not a synthesis reaction. It's a hydrolysis or breaking reaction. Okay, good. So now you have a data table, and you're looking at enzyme D. And what temperature would enzyme D most likely be denatured? Nice job. All right. Way to read the data, guys. Excellent. So if its optimum temperature is between 20 and 27, then you're looking for a much higher temperature in order to denature it. You're looking for something higher than this range, right? So then 45 is great because all the other numbers are within its effective range. So you chose well. Very good. Nice job. So which factor does not alter the rate of hydrolysis of maltose? Which one would allow it to work just fine? How much water is present? Okay, yes, I think that is definitely, that's a good example, actually. I like that. Good. All right. Okay. And this one, I won't ask you this, but I wonder if maybe you know what the answer is. Just try it. Something that binds to an enzyme and decreases the activity. Just follow the language. Pick the one that's most logical with your understanding of language. That's it, inhibitor. You got it. That's it. It's as simple as that. Follow the language in that one. Inhibitor would inhibit the reaction. Excellent. Good. And again, I'm asking this, but I won't ask it on the test. I just wondered if you know what this is. These inhibitors bind to enzymes in a location other than the active site to change its shape. Let's take this. Non-competitive, right? Yeah. And the reason for that is because a competitive inhibitor would be binding in the same active site and competing with the substrate. So there you go. You just learned something that the rest of the students didn't have to learn for this unit, but now you know. Wow, Emma, way to go. Almost done. And again, you won't have this for the test, but see how you. I will say allosteric is non-competitive. That's okay if you don't know it. I could probably have left it off. It's actually true, yes. So maybe before the AP test in May, we'll talk about this, but I don't know if we'll get to it. So we'll see. Don't worry about it for this test, though. Okay, nice job. I think one last one or a couple. Okay. Ah, this is a good one. You should know this one. This is a delta G question. So the graphs we just talked about, right? If you have a delta G, what happens if you double the amount of enzyme? It doesn't change it. Yeah, that's right. So if it was negative 20 to begin with, remember the interval on the graph? It's not going to change no matter how much enzyme is there, no matter how fast or slow the reaction goes. The delta G is always going to be the same. Okay, so that's a good one. That's a testable one right there. So if that taught you something just now, then that's a good thing. Excellent. Okay. One last one. So increasing the substrate concentration in an enzymatic reaction could overcome which of these? And I won't ask this, but you can just take a guess. Good, competitive inhibition, that's right. Because the more substrate there is competing with the competitive inhibitor, the more that substrate will win out and change the reaction rate. But don't worry, you don't have to, won't be on the test. Okay. All right, awesome job, ladies. Awesome. We are done, unless you have other burning questions for me. Oh, wait, we have to do the thing, right? I forgot to do the thing. We'll do the thing. There we go. Hannah comes in third. Yay! Joe comes in second. Spotlight on Emma. Woohoo! Okay. Excellent. Excellent. You all did fantastically well because you're here and participating. You are all winners. Are there any more questions? Any more questions for? Stop this. Stop that. There we go. Leave. There we go. Okay, sorry, here I am. I'm back. Yes, Hannah, question.
So is our test is tomorrow, but our graph also due tomorrow?
Are you in 7th period, Hannah?
Yeah, 7th period.
Okay. Right. So you guys' graphs are due, you just have to get them done before Tuesday because that's when your graphing activity is.
Okay, so it's because that's
okay.
a group project. Okay, that makes more sense.
Right. So you should prioritize studying for your test. Okay. And then do your graphs this weekend or polish them up this weekend. All right.
Okay. And someone mentioned something from AP Classroom. What was that we have to finish?
Oh, the only thing you need to do is the Albert IO mastery quiz.
Okay.
Right, which is due Friday for you guys.
Okay.
For everyone.
Thank you.
But it could help you on the test, so it would be good to get it done before.
Okay. Thank you.
You're welcome. You're welcome. You guys all good then? I'm assuming yes. Okay, I'm going to stop recording.